In frequency division multiplexing, we can also implement the analog hierarchy, in which we will have multiple multiplexers at multiple levels. Now here, if you look into this diagram, here we have 12 voice channels connected with an FDM, and here these 12 are multiplexed and these are further connected to another FDM. So these 12 are making 48 kilohertz channel, and which is connected to another FDM. So this FDM is taking 4 more groups just like this one. So there would be some other channels to coming to this FDM. After that, these will be connected to this FDM, each having 48 kilohertz, and all these would be combined to form a 240 kilohertz channel. And after that, in hierarchy, we will have third FDM and so on. So this can be implemented at different levels. We will have multiple FDMs, and these FDMs will be implemented in a sort of levels, in which each FDM will be connected to another super FDM, and after that super FDM, and so on. So ultimately, one FDM will combine a big number of channels in different hierarchies. We have one another example for frequency division multiplexing. It's example number 4. The advanced mobile phone system AMPS uses two bands. The AMPS is the 1G first generation cellular phone, and this was before the GSM. The AMPS uses analog signals, and for multiplexing it uses FDM, frequency division multiplexing. So it uses two bands. The first band of 824 to 849 megahertz is used for sending, and 869 to 894 megahertz is used for receiving. One for sending and second range is for receiving. Each user has a bandwidth of 30 kilohertz in each direction. How many people can use their cellular phones simultaneously? We have a range from 824 to 849 megahertz, 25 megahertz range for sending, and 25 megahertz for receiving. This is in megahertz. Now each user has a bandwidth of 30 kilohertz, not megahertz, kilohertz in each direction, 30 plus 30. How many people can use their cellular phones simultaneously? At one time, how many people can use cellular phones? Now, solution. Each band is of 25 megahertz. If we divide this 25 megahertz by 30 kilohertz, we get 833.33. In reality, the band is divided into 832 channels. Of these, 42 channels are used for control, which means only 790 channels are available for cellular phone users. So if we divide 25 megahertz by 30 kilohertz, we get 832, and out of this 832, 42 channels are used for control. So if we subtract this 42 from 832, we get 790. So 790 channels are available for cellular phone users. Means that 790 people can simultaneously use their cell phones connected with the amps network having these ranges of frequencies, and each user using 30 kilohertz. Next is time division multiplexing. Sharing of signal is accomplished by dividing available transmission time on a medium among users. This is used for digital signals, and for analog signal we don't use time division multiplexing. In time division multiplexing, each user is given a particular period of time to transmit the data. So we will have different time slots for different users in time division multiplexing. Here, if you look into this figure, we have four users connected with a multiplexer. These are identified by 1, 2, and 3, 4. In the channel, each user is given a particular period of time. So if you look into one is given a time, then after that 2, 3, and 4, and again 1. So 1 must send some data, and after that wait for 2 and 3 to take their time slots. Once they complete, again 1 will be given the time slot, and at receiving end demultiplexer read these time slots. Actually this must be synchronized with this multiplexer, and the time slots are utilized or forwarded to their corresponding destinations. Time division multiplexing comes in two forms. We have two forms of time division multiplexing. The first one is synchronous time division multiplexing, and the second one is statistical time division multiplexing. This one is also known as asynchronous time division multiplexing. First, synchronous time division multiplexing. The first one, the original time division multiplexing. This is actually the original time division multiplexing which we have studied now. The multiplexer accepts input from attached devices in a round robin fashion and transmit the data in a never ending pattern. The T1 and ISDN telephone lines are the common examples, and these two use synchronous time division multiplexing. Here we will have some users, and each user would be given some time slots. So if you look into this one is coming from A. So A is given some time slots, A1, A2, and A3. Similarly for B, we have B1, B2, and B3. Now if we look into the frames, in each frame A is given some time, then B is given some time, similarly C. So this one is a complete time slot duration for 3 users. So each user is given a time slot, and in this way the communication channel is shared among different users. Here we have another figure. Here we have 4 devices connected with a multiplexer, and if we look into these bits, suppose we are sending 1 bit. The time for transmission is taking only 1 bit from each user. So the first bit is from 1, then second bit is from 2, 3, and 4. It is completed. So again 1 will start, and similarly this cycle will continue until these devices stop their transmission. If one device generates data at a faster rate than other devices, then the multiplexer must either sample the incoming data stream from that device more often than it samples the other devices, or buffer the faster incoming stream. So we have two options. The first one is to give more slots to the speedy device, or to use a buffer at receiving side so that that buffer can store the data from a speedy device or device which is rapidly generating or sending data. So here in this figure we can see that the device A is sampled twice here, so given it has been given two time slots, and rest of the devices are given only one time slot. If a device has nothing to transmit, the multiplexer must still insert a piece of data from that device into the multiplexed stream. This is the disadvantage of synchronous time division multiplexing. It is a sort of limitation for STDM, the synchronous time division multiplexing. Here, this device is active, the rest of three are not active. So what happens, for each device there's a time, and if we look into the data, first block is okay in this time slot. Number one sends data, and the rest of the time slots are empty because these three devices are idle, they are not sending any sort of data. So only one input device is transmitting data, and rest of the time slots are sending zeros as idle data bits. We have an example for synchronous time division multiplexing. This is the figure. Here we have three users, A, B, and C. So now consider this figure. The data rate for each input connection is 3 kbps. So data rate for this one and the third one is 3 kbps, 3 kilobits per second. If one bit at a time is multiplexed, a unit is 1 bit. What is the duration each input slot, each output slot, and each frame? So here, what is the time for this one, this entire frame, and this single block in the frame for device A? So the first, each input slot, the data rate of each input connection is 1 kbps. This means that the bit duration is 1 by 1000 or 1 millisecond. The duration of the input time slot is 1 millisecond, same as the bit duration. So here this one is 1 ms. Then second is each output slot. The duration of each output time slot is 1/3 of the input time slots. Since we have 3 users, so it would be divided by 3. This means that the duration of the output time slot is 1 by 3 milliseconds. This one or this one or this one, for each user we have 1 by 3 milliseconds. Then the third one is each frame, the time for each frame or the duration of each frame. Each frame carries 3 output time slots. So one is 1 by 3, so for 3 output time slots it should be multiplied with 3. So the duration of that frame is 3 into 1 by 3 milliseconds, or 1 millisecond. So the duration of a frame is the same as the duration of an input unit. So duration for this frame or this one or this one, it would be 1 millisecond. Next example, the example number 6. The next figure, here we have a figure. We have 4 users, each having 1 Mbps. In the next figure, synchronous time division multiplexing is shown with a data stream for each input and one data stream for the output. The unit of data is 1 bit. 1 bits are given in each unit in the frames. The input bit duration, find the input bit duration, the first thing. So first check this one. The input bit duration is the inverse of the bit rate, 1 megabits per second. So the duration should be 1 divided by million, 1 microseconds, or 1 millionth part of a second. So this would be the duration for input bit. Here duration for the input, this 1 bit is 1 millionth of second or 1 microsecond, also for all these bits. Then the output bit duration. The output bit duration is 1/4 of the input bit duration, that is 1 by 4 into million, 1 millionth of second, 1 by 4 into mu second. It would be these bits, all these bits in the frames. These are actually time slots. Then third thing is the output bit rate. The output bit rate is the inverse of the output bit duration. The output bit duration was 1/4 mu second, so it would be 4 megabits per second, 4 Mbps. This can also be reduced from the fact that the output rate is 4 times as faster as any input rate. So the output rate is 4 into 1 Mbps. Actually here we have 1 Mbps for input bit rate, and for the output bit rate it would be 4 times greater than the input, so it would be 4 Mbps. This one entire frame, also all these 4 frames. Then last thing is the output frame rate. The frame rate is always the same as any input rate. So the frame rate is 1 million frames per second. We have here 1 megabits or 4 megabits, then it should be 1 million frames per second. Because we are sending 4 bits in each frame, we can verify the result of the previous question by multiplying the frame rate by the number of bits per frame. So if we look into the previous question, this thing can be solved by taking the previous example. So this was about the synchronous time division multiplexing. Now we are moving towards the statistical or asynchronous time division multiplexing. Statistical time division multiplexing. A statistical multiplexer transmits only the data from the active stations. Actually, there was an issue with synchronous time division multiplexing, that was here. If some systems are idle, Still, there were some time slots assigned to them, and this was actually the wastage of the entire bandwidth or the time slots during the transmission. So to avoid such type of case, we use the statistical time division multiplexing. If a workstation is not active, no space is wasted on the multiplexed stream because the time slots are given only to the active stations. Creates a frame containing only the data to be transmitted, and no empty slots are used during the transmission of data. In empty slots, usually we put zeros, so there would be no dummy zeros during the transmission of data. This is the comparison between the synchronous TDM and statistical TDM. Now, if we look into the lines, here we have 5 lines. The line A is transmitting A1 only one block of data, B is transmitting 2 blocks, C is transmitting nothing. This one is idle. Now here A is given time slot and this one got empty, but still it is assigned to C, and here to E this one is empty because at this time it is not sending something. Later it sends E2, so next time this one is filled. A is not sending something, so this one is empty. Now similarly for C, this one is empty. So these slots are wasted in synchronous time division multiplexing. Now if you look into the statistical time division multiplexing, here we don't have any empty slot, but there is one additional thing that identify the generator of slot or the owner of slot. So here the order was understood that first slot is for A, second slot is for B or must for B, then third slot must be for C. So this was actually understood, this order was understood. So here the order is not understood at the receiving end. So for that purpose, one additional flag is also attached with the packet or the slot that identify the owner of the slot or the sender of the slot. So here A1 is generated by this one is identified, then B is identifying line B, similarly D is identifying the line D. So this is the main difference between synchronous and statistical time division multiplexing. To identify each piece of data, an address is included. Here we can see that the addresses are included with these pieces. So we have data of A, then address of A, similarly data of C and address of C, and so on. If the data is of variable size, a length is also included. It is possible that we don't use fixed slots here. So for that purpose, we must also provide the length of that block here with the address. So it would be like this: data of A, length of A, and address of A. So this whole thing would be about line A or the device A. This type is better than synchronous, so it doesn't require a line over a high speed. The statistical time division multiplexing does not assume all sources will transmit all the time. We have seen this thing that it doesn't use any empty slots or doesn't entertain the idle systems. Since it is efficient, therefore it is good for low bandwidth lines, and usually it is used by LANs. So we can say that the statistical time division multiplexing is using the bandwidth in an efficient way. So this was all about multiplexing. you have any question, you can put your questions in the KCMS. Thank you.